So you've shelled out a ton of cash for the best equipment. You've designed your experiment down to the last detail, and then you look at the results, and the data's just wrong. It's a story we've all heard in the lab, right? But what if the problem isn't your expensive gear at all? What if it's something you can't even see? Yeah, let's really dig into that. It's the big mystery we're tackling today. Why is it that you can plan everything perfectly, use the best instruments money can buy, and still end up with data that's corrupted or just plain unreliable? Well, it turns out the answer is often hiding in plain sight. And that right there is the key. It's almost never the million-dollar machine that's at fault. Nope. It's usually some subtle, simple little mistake in how the whole thing is put together. These are the phantom errors that can haunt your data. And today, we're going on a ghost hunt. Okay, our first suspect is the very first decision you make: which measurement circuit to use. I know, it sounds super basic, but getting this wrong is one of the fastest ways to guarantee you're going to get garbage data before you even hit the start button. See, it all comes down to resistance. Measuring a device with a really, really high resistance is a totally different ballgame than measuring one with a very low resistance. And if you use the wrong approach for the job, you are walking straight into a trap. Let's take a look at circuit A. Here, we're forcing a known current through our device, the DUT, or device under test, and we measure the voltage across it. Seems logical, right? But for a high-resistance DUT, this is a total disaster. Why? Because your voltmeter isn't perfect. It has its own internal resistance. So by connecting it like this, you've accidentally created a second path for the corrective flow, basically sealing some of it from your DUT. Your voltage reading, it's going to be way off. Okay, so we switch over to circuit B. Now we're applying a known voltage and measuring the current. This completely solves our high resistance problem. But you knew there was a catch, right? If you use this setup on a low resistance device, you have to pump a huge amount of current through it just to get a voltage you can actually measure. And all that current, it creates heat. Enough heat, in fact, to literally change the resistance of the very thing you're trying to measure. You end up chasing your own tail. So the takeaway here is that there's no single best circuit. It's all about using the right tool for the job. The rule of thumb is pretty simple. Circuit A, where you measure voltage, is your go-to for low-resistance devices. And Circuit B, where you measure current, is what you want for the high-resistance ones. Match the circuit to the DUT. And wow, this slide really drives the point home that even with the perfect circuit, your choice of instrument matters a lot. What we're looking at here are two different current sources. That blue line, nice and clean. The red one, yikes. It's incredibly noisy, throwing out all these energy spikes that can totally corrupt your results. It could even make it look like a device is switching on when it really isn't. It just goes to show you, not all equipment is created equal. All right, let's move on to our next pitfall, and this one is really sneaky. We're talking about phantom currents. These are flows of electricity that have no business being there, but they can wreak absolute havoc on your measurements. And the most infamous of these is the ground loop. You know, in a perfect world, every single ground connection in your lab would be at the exact same 0-volt potential. But in the real world, that never happens. Tiny differences in potential between the ground plug of one instrument and the ground on another can create a closed circuit, an accidental path for current to flow. This loop then acts like a giant antenna, just sucking up all that 50 or 60 hertz hum from the power lines on the walls. And this slide shows a real-world example of just how bizarre these things can get. A lab was being driven crazy by noise they just couldn't track down. The cause? Well, a cryogenic dewar was sitting on the concrete floor. That floor was touching a metal table, and that table was holding a grounded instrument. The dewar, the floor, and the table created this huge, invisible ground loop. I mean, what textbook would ever prepare you for a circuit like that? And that's what makes these things such a nightmare to find. It's less about being an electronics expert and more about being a detective. As the source material says, you really do have to get creative sometimes. It takes patience and a methodical approach where you only change one thing at a time until you find the culprit. And ground loops aren't the only phantoms in the machine. Say hello to leakage current. Especially in AC measurements, the cables you're using can act like tiny little capacitors. It's called parasitic capacitance. And as you can see here, that can create an unwanted side road for your current to leak away from your device. So the current you think you're measuring isn't the current your device is actually seeing. So let's say you've done everything right. You picked the perfect circuit, you hunted down every last ground loop, your analog signal is pristine. But the second that signal gets converted into ones and zeros, a whole new set of traps is waiting for you. We're now in the world of data that lies. It's a heck of a question, isn't it? But the answer is, oh, absolutely. Yes. Once a signal is digitized, it can still paint a completely false picture of what's really happening. And this isn't about a software bug, it's a fundamental trap of how digital sampling works. The phenomenon is called aliasing. The best way to think about it is like watching a car's wheels in a movie. You know how sometimes they look like they're spinning backwards? That's a visual alias. Same thing happens in electronics. If you have a signal at, say, 1,000 hertz, but you only sample it 800 times a second, your computer will mistakenly see a totally different, much slower frequency that doesn't actually exist. It literally invents a signal that isn't there. So how do we stop the data from lying to us? How do we make it tell the truth? We sample faster, a lot faster. As you can see here, by taking a whole bunch of samples for every single cycle of the wave, we collect enough data points to perfectly reconstruct the original signal. We get to see its true shape, its true frequency. Now, this isn't just a good idea, it's basically a law of physics for digital signals. It's called the Nyquist theorem. It is the golden rule. To avoid aliasing and get an accurate picture of your signal, your sampling rate has to be, at a bare minimum, double the highest frequency you expect to measure. And honestly, in practice, most engineers will sample 5, even 10 times faster, just to be absolutely safe. Now, beyond aliasing, the big fight in the digital world is against noise. And the good news is, you've got a whole toolkit at your disposal. Things like proper shielding on your cables act like armor against outside interference. You can use filters to chop out specific frequencies you don't care about. Signal averaging, where you take tons of measurements and average them together, is great for smoothing out random noise. And using differential inputs is a really clever trick where your amplifier can automatically subtract out any noise that's hitting both of your signal wires. So let's just boil this all down. Getting clean, reliable, accurate data really comes down to these 4 things. 1, always match your measurement circuit to the resistance of your device. 2, put on your detective hat and hunt for those invisible ground loops and leakage paths. 3, when you go digital, sample way faster than you think you need to, at least twice the highest frequency. And finally, number 4, be methodical. If you have a problem, just change one thing at a time. That's the only way you'll know it fixed it. Look, at the end of the day, your data is only as good as the measurement you took. All the fancy analysis in the world doesn't mean a thing if the initial number was flawed. The integrity of your entire experiment starts the moment you connect that first wire. So go take another look at your setup. What invisible errors might be hiding in your data right now?